All right. Questions? Anything? You got this? Let me leave it up there for a couple of seconds. I'm going to work number 6 also and see if that helps you. It's kind of strange. Usually they go from like 0 to 3 or something like that. But on this one, we always put the largest number on top, small number on the bottom. We always start with the top number minus the bottom number. And that's really the fundamental theorem of calculus, is how we derive this. The fundamental theorem of calculus says that when you have a definite integral, you're just going to substitute in the top value minus the bottom value. And that will give you the area. And this is the big breakthrough that both Leibniz and Newton had when they discovered this stuff. Why are you upside down? All right, here we go. I'm going to erase it. Anybody want to see it anymore? Speak up or forever hold your peace. You can unmute yourself if you want. I hear no objection. Going, gone. Okay, number 6, interesting little terrible problem. But these kind of the brain busters, that's what makes them fun. This is the integration of 0 to -3, 4x. They could have written this as the cube root of x, but they wrote it as x to the 1/3. If it was the cube root of x, you'd want to simplify it to this form anyhow. Dx. All right. So the way I did it is I took the derivative of this. So this would, 4 we can just take out. That 4 is going to stay. I should have closed my door. I didn't think about it. So this is 4. That's going to stay. And then this is going to be, if you wanted these things, x to the 1/3 plus 1. So that would be 4/3 over 4/3. We can bring this 3 up to the top. Kind of a quick way of doing it. Or we could just say we're multiplying it instead of 4/3. We're multiplying by the reciprocal of 4/3, which is 3/4. You can think of it that way too. Huh? You're just using the reciprocal. If this is a fraction, you multiply by the reciprocal. And this 4 will cancel out 4, so we end up with 3x to the 4/3 from 0 to 3, -3. So if we put a 0 in here, this is just going to become 0 minus. That's always a nice number to substitute in. So what I did on this one is I wrote it as, okay, I'm going to put in a -3. This should be 3. And then I wrote this as power over index. So this is the cube root of something to the 4th. And this would be -3 to the 4th. Let's just put it underneath there. Okay, again, another messy mess. So this is -3 times the cube root of 81. And 81 we could break down into what? 27 times 3. And the cube root of 27 is 3. So we got -3 times 3 times the cube root of 3. So I end up with -9 cube root of 3. Or if you convert it, look up the cube root of 3 and you multiply it by -9, you get about -12.98. So you're dealing with, right here, you're dealing with a lot of algebra, taking the cube root, 27 thirds, trying to break that down. This becomes a perfect cube root right here. Comes out as a 3. And then this 3 stays underneath. So that's what makes these problems hard. It's not really that they're so difficult. It's just that sometimes you run into a lot of fractions, radicals, things like that that make it a little tougher. So I do one more off this page. You tell me which one you'd like to see, and I can try it. Is there a particular problem you'd like to look at? Chris, anything? Delilah?
Could you do number 5?
5, okay. Let's, can I erase this? Okay?
Yeah.
Okay. I want to make sure everybody's got it. Okay, number 5. Well, fortunately, the boundaries aren't bad, 0 to 1. That makes it -1. That makes it easier. But we've got a pretty long problem here. So this whole thing is, we're going to kind of find out about this dx. I'm going to kind of work a couple of things on coming up on the u subs to show you. And then next class, we'll do some stuff on the actual u subs. Okay, so let's go ahead and integrate this x to the 6 over 6 minus 4 times x to the 4 over 4 plus 4x squared over 2 plus 4x. Because when we do u subs, you have to use your differentiation also. So you have to remember those things that you have a tendency to want to forget. And this is from 0 to -1. Am I writing it so slanted? I don't know. Okay, so we're going to substitute a 0 in here. Let's say that would just be 0. This would just be 0. We can cross off these 4s, might help. And we could divide this in here and make that a 2. That still would be 0. And this would be 0. So that's going to come out 0. Minus. Now we're going to put a -1 in here. So -1 to the 6th power is a +1. We're going to put this in a parentheses. It's this whole thing minus this. So this is a -1 over 6. If I make a mistake, let me know. I'm going to make this a minus. Okay. I'll put a -1 here. -1 to the 4th is a +1. Huh? Okay, plus this is now 2x squared. So -1 squared is 1 times 2 is 2. Plus 4 times -1 is -4. All right. So we're out of all these negatives. That's a -7 and 1/6. These are all negative. No, wait. -5 and 1/6. Add this, this, and this. Check, check. Plus 2. I'm coming up with, this is a -3 and 1/6. But then you had the negative outside, so a negative times a negative is a positive. So I'm coming up with a +3 and 1/6, which is 3 and 1/6. That would be 18, 19, 6. That is not correct. Can you go? Excuse me? Right here?
1/6 should be positive.
Yeah, you're right. That should be positive. What about this one? This was positive, but then we had the negative. You're right. This should have been a negative 1 to the 6th power. It's even power. Yeah, 1/6. So let's see how that changes our calculation here. We got negative 5 plus 2 1/6. Negative 5, 2 1/6. I'm going to change this to 4 6/6. Gives me 3 2 5/6. And this would be negative. Still stating that this should have been a negative 4. Okay, so this should come up to negative. Oh, that was okay. This combination, however you calculate it, should be a negative 2. And you could use your fraction key too. Negative 2 5/6, which is a positive 2 5/6, which is correct. If you're having a little trouble understanding that, let me do that another way. Let's change this to improper 13/6. I multiply this side by 6 over 6, so that gives me negative 30 over 6 plus 13 over 6 is negative 17 over 6. Wait a minute. Yeah. So you could have looked at this as negative 17 over 6 also, and it was minus that. So that came out a positive 17 over 6. Same thing. Thanks. Yeah, this is where I messed up. And that's what's hard about these problems is if you screw up here just a little bit, you don't put the right power down, or you mess up over here where you messed up on a sign, and it looks like your whole answer is totally wrong, you know, and there's just a little tiny mistake or something, but it multiplies itself through the problem. Okay. All right, I'm going to show you a little bit of the next section because the next section is a little bit tougher. Oh, wait a minute. We got some problems. You had a backside to this, didn't you? Did you have the area between curves?
Yes.
Oh, okay. 4.4. All right. So there's 4 problems on this page. Is there one that you want to see? These get pretty crazy. I don't even know what I'm doing here. All right, well, let me take a look at the first one's fairly easy, but let's look at problem number 2 on the back side. I forgot about these problems too. These are probably the harder ones. So the problem that's on the top, it's always the top minus the bottom on this thing. So you're going to go to the boundary on this thing is from, it says calculate, does it give the boundaries? You know the boundaries on these. Yeah, but they didn't give you numbers. Well, you can't do them without numbers.
Would it be the x squared and the 2x squared minus 25?
Oh, yeah. The way we calculate the boundaries is this. First, we got to figure out the boundaries. You're right. So to figure out the boundaries, we're going to say that the one equation, x squared, equals the other equation. So we set the 2 equations equal to each other. And it didn't really matter which one you wrote first. And it would have been easier to write the other one first. But anyhow, we can set these 2 equations together. X squared equals 2x squared minus 25. And then what we're going to do is try to solve this. So we're going to bring this x squared over. We'll set this to 0. Bring this over. And so we have 0 equals x squared minus 25. And then what we're going to do is try to solve that. That's a difference of squares. x and x. You know, these would come out probably quadratic, and you just got to solve them. 5 and 5, plus and minus. So x plus 5 equals 0. X is -5. X minus 5 is 0. Bring it over. X is 5. So there's our boundaries now. Now we have our boundaries. 5, -5. Yeah, so on all these problems, if they don't give you the boundaries, you just set the two equations equal to each other, and then you're usually a quadratic, and you got to solve it. These should all factor where you don't have to use the quadratic formula or something. They should come out nice numbers. If you're getting a real strange answer for your boundaries, your boundaries should be simple numbers like 5 and -5 and something like that. So, okay, now we're going to take this first equation because this is the top. If you mess up and you put this one and you switch these, it's x squared minus this whole thing. And then this whole thing is to the dx. I'm going to just kind of scoot over the dx. But this, rather than putting in another brackets and all that. Okay, if you mess up and you put the 2x squared minus 25 first and then the x squared, the only difference is that your answer will come out negative. And if it comes out negative, we always are looking for a positive answer, so you just change it to a positive number. You get the right number, you just won't get the correct sign. Okay. So what we want to do also on this thing is before we jump in and start taking the integral of it, we want to simplify it. So this is going to be, I'm just going to write it up here, x squared minus 2x squared plus 25 dx. And then we could just kind of put the x squared in negative, 2x squared is negative x squared plus 25. And that's what we want to take the integral of. There we go. So now we got it in the right form. And now we're going to just substitute in the 5. So at the same time, I'm putting this 5 in here, but I'm going to calculate. This is negative 25 plus 25. Oh, wait, I haven't taken the integration of it yet. I haven't integrated it yet. Duh. Okay, let's integrate it. Okay, this is going to be negative x cubed over 3 plus, would have been a lot easier the other way, I'm going to tell you. 25, they would have both come out 0. 25x. Okay. From 5 to negative 5. Yeah, don't forget to take the antiderivative. I mean, that's the whole idea. Yeah. Sorry about that. Big, stupid mistake. Okay, I'm going to put the 5 in here. So this will be a negative 125 over 3 plus 100. 5 times 25 is 125. That quantity minus, now I'm going to put a negative 5 in here, which comes out to be 125 over 3. Should come out positive when I put it in. This is negative times negative. And then I put in negative 5 in here, which is minus 125. So I end up with, I'm going to distribute out that minus sign. I got a negative 125 over 3 plus, and you might do this part on scratch paper or something like that. I just kind of write it down to show you. Plus 125. So I ended up with 250 minus 250 over 3. So that came out to be, I can multiply this by 3 here, get a common denominator, 3 on the bottom. So that'd be 750. I don't know if you can see this 2L over 3 minus 250 over 3, which comes out to be 500 over 3. And that's how I left it. I didn't. You could change it to a decimal if you wanted to.
Mr. Mitchell, 125 divided by 3 is, oh wait, just kidding.
Yeah, I didn't divide it. I just, what I did is I added this and this together to get the 250. And then I just got a common denominator. You could change them to decimals. You know, if you wanted to change this to a decimal right away and make it 250 minus what it would be, what, about 83 or something like that, 83.3 or something. You could do that. That's fine. You can leave them in decimal form. I'm toying with the answer with that final example being a multiple choice type test, but I don't know yet. I'm toying with the idea. Make it a little bit easier for you guys. At least if you don't know how to do the problem, you can take a guess, you know. Okay, so that's how these are done. Terrible, huh? It's just a lot of calculations, you know. So when you don't have the boundaries, because most of the time they do give you the boundaries, you know, but if you don't have the boundaries at all, and you want to know where do these start to overlap, you know, like this one was kind of coming here and the other one was going down here like a smiley face. This was -5 here for X and this was +5. We don't need to know the Y value. We just need to know the X values. And so we figured that out, and put them in and do a calculation. And really, this part isn't so hard right here, taking the integral. It's this part on down that's, if you like to change these to decimals right away, you know, it won't be quite as exact, but it'd be pretty darn exact. You know, you could change it to working with fractions instead of fractions. You can work with the decimals. Messing around with it. Okay. Anyhow, that's that. Let me show you a little bit of U subs. Let me grab my book, and we take a little bit of U subs.
So is that going to be 4.5?
Yeah, that's the next one coming up. I'm going to go over it again tomorrow. We have a little bit of time. I want to show you, in case you wanted to start on it. But we'll basically do this tomorrow. But let's see, where is U subs? There's two strategies. There's U subs, and then there's parts. We didn't get into parts. I love parts. It's a little bit more difficult, but we didn't quite get into it. But there's sometimes we run into problems. We have to use U subs. I'm going to show you this problem right here. What happened is this problem is a bit more complicated than what we've been doing. Because this problem kind of was like a Bab's problem or something, maybe originally, or something like that, you know? So it would, you know, instead of having just a nice little integration of 2x dx or something like that, we've got this more complicated thing. So what we do is sometimes we say, okay, we're going to let U is just going to be an arbitrary letter, but we usually just use the letter U. Here. Pen's messing up. Are you messing with me? Trying very hard to write this. Okay, U is going to stand for, and that's where we have to kind of take a guess. What is U going to stand for? And we're going to let it stand for 1 plus x squared. So now what we're going to do, now we're going to see the importance of this dx. Because up to this point, we kind of ignored it. We weren't really thinking about it. But now we're going to differentiate this. We're going to do the differentiation of this. So du, I'm going to write it a little more formal. Chris, what are you doing? Are you messing with my little thing? Over dx equals, how do we do the derivative of this? What's the derivative of 1? 0, huh? And the derivative of x squared is 2x. So what makes it a little harder to do this is we haven't done differentiation for a while. So now all of a sudden we're differentiating, and now we're going to put the dx. We're going to, when we do this, we're going to multiply both sides by dx. Here and here. So this is a more formal way of writing the derivative, du over dx. And we get du equals 2x dx. And if you look up here, Chris, okay, so we get, in place of this 2x dx, I'm going to substitute, I don't know, this pen is going crazy, it's gone. It's hard to write with this. I'm going to write du, going to try to write, I have to take this up tomorrow. What is the deal here? Over u. See, now all of a sudden this has more meaning to it. This stands for du, and this stands for u. And we're going to explain this a little bit more tomorrow. So this is maybe more or less in the form one over u du. I'm sorry, this is falling apart here. So 1 over u would be ln u plus c, and then we just substitute in what u stood for. So we're talking about this more tomorrow. This thing is going crazy. I think somebody's messing with me. Okay, well, anyhow, we're talking about it tomorrow. Not funny. All right, so mañana, I think that'll cover. Do you have any on today's that you want to see? One more before we shut down. Anybody? Your chance to ask. Like I said, on these problems on 4.4, those are going to be where it says 4.4, the top area between curves. It just, you run into a lot of fractions or decimals on them, so you just got to be a little cautious. But that's the kind of the neat part about calculus is we can actually find the exact area between two curves, you know, like that one we just did. To find this area, how else could we do this? It'd be very difficult, you know, because you basically have two parabola-shaped things. Not a very easy thing to do. So this is kind of the power of calculus, even that one like this, where you just have a straight line going through it, and you're trying to calculate this area in here. Not so easy to do, you know. where would you use something like this? Well, you probably have a lot of applications to it, especially like if you're trying to figure out how much volume of air is inside a dome stadium, between the stadium and up here. How much brains you can put in your head. So you can have your head here, here's your face. And you can put how many brains do you have in your head? So you can do all kinds of things with this. All right. I'm going to sign off. If you have any other questions, you can always text me. And a couple of students have, and they've asked for some information. I can usually try to give you some over the internet that way. Or if you have if a question comes up on this or any other quiz, you can ask tomorrow on our Zoom. I'd be glad to work. Maybe there's another problem here you see that you didn't get to it, and then you're going crazy on it. I can probably help you tomorrow then. All right, signing you off. Have a good day. Enjoy the day. Let's see, I need to